Okay, here's an example problem for the exam 1 review. It says find and classify all of the critical points of the function h of xy equals x cubed plus y cubed minus 3xy. So the idea behind our approach, our goal will be to find the critical points of our two-variable function in its domain. So its domain, because h is a polynomial in two variables, its domain is all of R2, so the entire real plane. So every pair of real numbers can be fed into this function h. And also, we see that this domain has no boundary, so we don't need to check any boundary conditions like we did in single variable calculus. Any possible maxima, minima, critical points will happen at points in the domain where the gradient vector is 0. So that's what this condition means. That the gradient of f at these points is the 0 vector, where, if you recall, the gradient vector is the vector whose first component is the partial derivative of f with respect to x, and the second component is the partial with respect to y. So we'll compute these two partial derivatives. So we'll compute this gradient vector. Oh, sorry, these should be h's, of course. So we compute the gradient vector and we get the derivative of this first term is 3x squared. The derivative with respect to x is 0, and then minus 3y. And then 3y squared minus 3x. And I'm looking for those points x and y such that both of these equations are satisfied. And what that looks like is the intersection of two curves. So the set of solutions is the intersection of two curves in the plane. So we'll solve that over here. The first curve is, so maybe I'll call this equation 1, equation 2. So equation 1 gives that we want 3x squared minus 3y equals to 0. Well, that just means that y equals to x squared. So that's the usual parabola in the xy plane. Equation 2 gives 3y squared minus 3x equals 0, which means that x equals y squared, which is the reflection of the usual parabola about the line y equals to x. So that looks like this. So here's R2. That's the entire real plane. And now we have our parabola for the equation 1. Y equals x squared. And then we have the reflection x equals y squared. So a solution to both of these equations means that you have a point which lies on both of these curves simultaneously, which is to say that you have an intersection. So there are 2 points of intersection between these two curves in the plane, which is x equals 0, y equals to 0, and x equals to 1, y equals to 1. So the conclusion of this analysis is that there are 2 critical points. So H has 2 critical points in its domain. They are zero, 0, and 1, 1. To determine if these critical points correspond to a saddle point or a maximum or a minimum, what we'll do is we'll use the derivative test. And the derivative test, again, in multivariable, again, looks like a table. So here's this column is my list of critical points. I have 2 of them, 0, 0, and 1, 1. We can look at the sign of the determinant, which means, if we remember what the derivative test says, is the determinant is the determinant of this 2 by 2 matrix. Sorry, these should all be H's. Hxx is the second derivative, so that's 6x. Hxy is, take the y derivative, so you get minus 3. Get minus 3 here again, and 6y. So if I evaluate this determinant, oops, there should be a determinant of this. So the determinant is equal to 36x times y, and then 3 minus signs, so minus 9. So at the point 0, 0, we get this is equal to minus 9, which is negative. The sign of the second x derivative is 0. So by our derivative test, because the determinant has negative sign, the critical point is a saddle. And we look again at the critical point 1, 1. If we plug in 1, 1, we see that we get something positive. 36 minus 9 is something positive, and all we care about is the sign. The sign of the second x derivative is positive because it's 6. And so we conclude, again by the derivative test, that the critical point 1, 1 must be a minimum. And that's how one does this analysis.